Right, so I'm going to be presenting ALFRED, which is virtual memory for intermittent computing. It was presented at SenSys 2021, and it's by a group from Politecnico di Milano. Brief introduction to intermittent computing. It applies to embedded systems relying on harvested energy. Now, because this harvested energy isn't constant, your device isn't always on. And so if you have a program, most programs won't be able to complete during the short times that your device is actually powered. So if you were to plot some measure of progress versus time, you're going to get something like this, where your program makes progress, and then suddenly you lose power and you lose all of that progress. You've got to start from the beginning, and most programs will never complete in this sort of situation. So what you need to do is frequently you need to save your volatile program state into non-volatile memory so that when your device powers back up again after losing power, you can continue from the same point and actually reach completion eventually. So yeah, intermittent computing requires frequent checkpointing of your volatile program state, which includes volatile memory and registers, to non-volatile memory. Now, when you write your program, you can make the decision to write any data to either volatile or non-volatile memory. Uh, they both have their advantages and disadvantages. The primary disadvantage of non-volatile memory is that it requires a lot of energy to write to these types of memory. And so what ALFRED does is it makes this mapping automatic. It takes that decision out of the programmer's hands and decides which variables to write, where to write them, and when to write them to volatile or non-volatile memory, as the case may be. And that's really where the virtual memory comes in, which was mentioned in the title. It has nothing to do with what we normally understand as virtual memory in a system with a memory management unit and an operating system. It's just, in this case, an abstraction that makes the destination of a variable transparent to the programmer. So ALFRED decides this mapping. The aim is to minimize non-volatile memory use because of the higher energy required. And it makes these decisions at compile time. So you don't waste, again, time and energy at runtime to make these decisions. And as for why it was named ALFRED, it's because of this. I don't think this counts as an acronym, but this is what it stands for, I guess. Um, moving on. So let's start with write operations. The principle for write operations is to target non-volatile memory as soon as data is final, compared to the next checkpoint. So if you look at the program here on this left-hand side, you have your computation interval, which is all of the computation that happens between two checkpoints, right? Um, so let's say you write something to A, right? And after this statement, A equal to A plus 1, you notice that you're not writing to A. The value of A isn't modified. So when you're writing A over here to volatile memory, you're writing the same value that you eventually write to non-volatile memory during your checkpoint. And so the instructions in red are essentially redundant, right? You can actually skip one of these, right? And so what ALFRED will do is, once this data is final, right? Because it knows that A is not written to again, it'll store A directly in non-volatile memory because its value is final. And the checkpointing stage doesn't then need to write A again to non-volatile memory. And in fact, if you do this with all variables, your state save operation only needs to save registers. And so the converse is performed. Sorry, going back, it does introduce a new issue over here when A is used again, but that's addressed in a couple of slides. So moving on to read operations, um, the converse is applied. So you only read data from non-volatile memory when it is needed. So in this case, right, before applying the transformations, your restore operations will read all your uh, volatile memory state from all the states saved in non-volatile memory into volatile memory. So it'll load the non-volatile value of A into some register and put it back into volatile memory. And when it's used, it is loading that value from volatile memory into a register once again. So again, these operations are redundant. So what ALFRED does is it'll load A from non-volatile memory when it is needed, right? During its first use within the computation interval. And so once again, if you do this for all your variables, your restore operation only needs to restore registers. So I had mentioned during the write operation transformation that there is a problem here, right? Non-volatile memory is more expensive, is more energy intensive to read and write. So if you stored your final value into non-volatile memory and subsequently you're using that same variable again, you're going to have to read it from non-volatile memory, which is going to consume a lot of energy. So instead of that, it might be worth saving a copy of that data to volatile memory. And so you do incur a cost in that you're writing this variable twice into non-volatile, once into non-volatile, once into volatile memory. But then you're reading it only from volatile memory. And so you need to make a decision on whether you want to do this or not. And that really depends on hardware characteristics. So what is the actual energy cost of reading non-volatile memory? And also how many read operations do you have in the computation interval after the value is final, right? This should actually be A, not A and B. Sorry about that. Now, there are a few compile time uncertainties that need to be addressed. The first is memory uncertainty. So if you have a loop, for example, you might be addressing different memory locations in the same statement, right? So in this case over here, A of I, the address pointed to depends on the value of I, right? Now, the insight here is that we don't really need to know the exact address in this case. We only need to know whether uh, statements within a computation interval are addressing the same location. And so all we need to do is tag each memory access. And so here we find out that, okay, these two statements are accessing the same memory location, but this one is different. And so once we know that, we can apply the transformations on read and write operations mentioned earlier. The next uncertainty is based on control flow. So this example is based on loops, but it's a similar principle that you can use for conditional statements like if else or case. So in this case, so remember, we want to write to non-volatile memory on the last, uh, for the last write in within a computational interval. And we want to read from non-volatile memory for the first read of that variable within a computational interval. So in this case, right, whether it's the first or the last access depends on the value of I. So we don't know where to load some from over here. And we don't know where to store some uh, in this line. Now, if we were to take a very conservative approach, we could load it from non-volatile memory and store it back to non-volatile memory on every iteration, but that's obviously going to consume a lot more energy, even compared to what we had initially without Alfred. So instead, what Alfred does is it introduces these kind of dummy accesses, right? Um, Obviously, sum equal to sum is not a statement that has any impact on your program semantics, but um, it solves the issue of when to load or store to non-volatile memory. And so within the loop, you only access volatile memory. Okay, so Alfred introduces some intermittence anomalies as well that need to be taken care of. These intermittence anomalies are caused by re-execution of non-idempotent code, which is code that will behave differently if it's executed twice instead of once. So um, let's look at this computational interval here. Uh, so when we load A from non-volatile memory, uh, it's initially 0 in this case. We increment it, and uh, when Alfred finds out that A equal to temp is the last operation to write to A, it will store it to non-volatile memory. So because it's been incremented, its value is 1. And uh, y equal to f of A should use the value 1, right? So this is normal continuous operation. But if there's a power failure before this state save operation here, right? When the device restarts, what happens is uh, we wrote A equal to 1 to non-volatile memory here. So when A is loaded here, it reads a value of 1 and gets incremented, writes 2 to non-volatile memory, and y equal to f of A will read the value 2. Whereas in a normal continuous operation, it should have been 1. So this is obviously wrong, right? So the way that Alfred solves this is by creating 2 copies of each variable in non-volatile memory. The first is is exclusively for reads, and the second is for read write. And so on the first read within a computation interval, it will read from AR, which is 0. And so this for initially I'm showing you the situation with continuous power. Now when it stores for the final write within a computation interval, it'll store the value to ARW, the read write location. So it stores 1, and for all subsequent reads that are not the first read, it'll load from the read write location as well. So this is continuous execution. Now, if we lose power here, at the same location as previously. Remember on restart, uh, your ARW is 1, but it's still going to read from AR, which is 0. And so you're going to get the correct execution that you expect with the increment and reading back the value of 1, which is what we had initially. So moving on to evaluation, important thing to note is that they use system emulation, so they don't actually evaluate this on actual hardware. The reason for that they give is that it's difficult to model intermittent energy. You're not going to get uh, the same pattern of harvested energy over multiple runs. They also compare only to systems that explicitly insert checkpoint uh, checkpoints in their code at compile time. It can't work on interrupt trigger checkpoints because ALFRED needs to know the duration of or it needs to know what a computation interval is, right? Whereas if it's interrupt trigger, that's non-deterministic. They use 3 benchmarks from the MyBench2 benchmark suite, CRC, AES, and FFT. And there are a number of baseline combinations based on 3 dimensions. So memory configuration, volatile and non-volatile. Some systems will write all of their data to non-volatile memory. And so they will only save registers and restore registers at checkpoints. That's where non-volatile comes in. Volatile is similar to what we discussed earlier. Um, checkpoints can also be inserted at different locations, either function return or every function return or loop latches. And checkpoints can be executed either always, which is what execute means. So every time a checkpoint is inserted into the code, it will actually be executed, versus in probe, where just before actually checkpointing and saving your data to non-volatile memory, you probe your system, you see how much energy you have left. If you think it's enough to reach the next checkpoint, then um, you don't actually create the checkpoint in that case. So obviously they don't evaluate their system for every possible combination of these dimensions. They actually evaluate it over 3. I'm going to go over 2 of those in the interest of time. So let's talk about energy consumption first. So this is for the combination of volatile, probe, and both loop latch and function return placement of checkpoints. And so FFT is the most computationally intensive of the 3 benchmarks they chose. And therefore, you see the biggest gains for FFT, right? Orders of magnitude less energy used compared to CRC and AES. But in every case, they do use less energy compared to the baselines. This again, sticking with energy consumption for a different configuration. This is non-volatile, so uh, since non-volatile, execute and again both loop latch and function return for checkpoint placement. Again, significant reductions in energy consumption. In this case here, you can see for CRC, if they use function return checkpoint placement, CRC actually doesn't complete in the baseline because it's not the way the code is the way the code is written for these particular benchmarks. It's presumably just one large function, so doesn't actually complete. Um, so moving the clock cycle, which is obviously a good standard for performance. Once again, FFT sees the biggest gains, but across the board, um, Alfred uses much fewer clock cycles. Um, this is a volatile probe in both loop latch and function return case. Um, Similar for the non-volatile execute and loop latch function return combination. And the final thing they measure is the number of restore operations. So um, this is kind of a good overall measure, right? Because the fewer restore operations you need, the fewer times you lose power, the fewer restore operations you need, the faster you complete your overall computation. And so once again, so these are the two same baselines as I mentioned earlier. Significantly fewer restore operations required for Alfred. And so to conclude, Alfred removes the need for a programmer to manually map uh, each variable to volatile and non-volatile memory. Alfred does it at compile time and results in a significant reduction in energy consumption and also much fewer restore operations required to complete workloads. Thank you.